Welcome to the application of derivatives, and we're going to learn today L'Hopital's rule. L'Hopital's rule is used with indeterminate forms, and I'll show you what that is, but an indeterminate form is when you have 0 over 0 or infinity over infinity. Only works when that happens, and we're looking for limits. So erase that. Alright, so John Bernoulli discovered a rule using derivatives to calculate limits of fractions whose numerators and denominators both approach 0 or infinity. The rule is known today as L'Hopital's rule after Guillaume de L'Hopital. I hope I said his name right. He was a French nobleman who wrote the first introductory differential calculus textbook where the rule first appeared in print. So basically, we're going to kind of do a little bit of review of limits. But before we go any further, this only works if you have 0 over 0 or infinity over infinity. If this case is not here, L'Hopital's rule does not work. So previously we've seen problems like this where we have the limit as x approaches 0 of sine of x over x. And before, what we did was we first always substitute. So if I did the sine of 0, the sine of 0 is 0, and if I put 0 here, I have 0 over 0. When it's like this, we had to do something to find the limit. Well, in this case, because we had nothing else to do, you guys used to graph it, look for the table, then we used to ask, and we'd approach this number really close, so we do 0.01, 0.001, 0.0001, or we'd go to the negative way, negative 0.0001, and then we'd see what this was approaching. Okay, that's how we first learn limits. What is your y approaching when you are getting very, very close to 0? Then we also learned, okay, what if we had this and we plugged in the 3, because you always substitute first, and I get a 0, and I plug a 3 here and I get 0 over 0. Well, maybe we can try factoring. So we learned how to factor, and we said, okay, this is a limit as x approaches 3, and then we factored it and said this is x plus 3 times x minus 3. And then this one was x minus 3, x plus 2. And then we saw this canceled, so this is the same as saying the limit as x approaches 3 of x plus 3 over x plus 2. And then when we got it in this form, we could actually substitute it in, and we'd end up with 6 over 5. Okay, so this is things we did before. We also did other things, and I'll kind of review them here. These are things we've done before to determine limits. We substituted first. This is the main thing. You always substitute first. Okay, don't skip this, because if you do not get the 0 over 0 or the infinity over infinity, then L'Hopital's rule does not work. We also graph the equation and use the table. That's what I demonstrated above. And then when we had this 0 over 0, this indeterminate form, sometimes we factored the numerator and denominator, which I already illustrated. Then sometimes we rationalized the numerator if we had a radical. And then we also simplified complex fractions. So these we had done before. Other ways we had done limits is if we saw a horizontal asymptote, we used the 3 rules. And when x was approaching infinity or negative infinity, and we found what the limit was doing then, and then we looked for vertical asymptotes when we got a number over 0. So this is a review that we did earlier this year, and I just wanted you to have it for your notes. Now, when we do L'Hopital's rule, we have to first of all figure out what this rule is and how this, I think, is one of the best ways to find limits. Well, L'Hopital's rule goes as follows. Suppose you have f of a equals g of a equals 0. So they're basically talking about if I have a fraction f of x over g of x, and I plug in whatever x is approaching to. So I'm doing the limit as x approaches whatever, a number, and in this case they called it a, that if I did f of a and I did g of a, so if I plugged in the number here, I'd have f of a over g of a, and it would be 0 over 0, then we can actually do the following. We can actually take the derivative of the top and the derivative of the bottom, and then figure out the limit that way. So if I do this, and take the derivative of the top, and we keep going and take the derivative of the bottom, we can actually find the limit. So this is kind of a neat way to do it. So that's a cool way. And the reason why I didn't show you this before is because we hadn't done the derivatives. Now here's something that is very important, using L'Hopital's rule, very important. Here I have x approaches a of f of x over g of x. By using L'Hopital's rule, continue to differentiate f and g so long as we still get the form 0 over 0. So you can keep doing this and keep doing this and keep doing this as long as you keep getting 0 over 0. Once one of these changes that you come up with a number, you have to stop. So basically this is saying once you get a number on the top or bottom in your numerator or denominator, stop, because then it doesn't work anymore. Okay, so that's why this is very important. But as soon as one or other of these derivatives is differentiate from 0, we stop differentiating. L'Hopital's rule does not apply when either the numerator or denominator has a finite non-zero limit. Meaning, if I hit a number, I have to stop. Okay? So steps to using L'Hopital's rule. One is to always substitute the number that you're approaching first. So you'll have 0 over 0 or infinity over infinity. Okay? The second thing is you're going to take the derivative of the numerator and then you're going to take the derivative of the denominator. If you still continue to get 0 over 0 or infinity over infinity, keep going. And what I mean by that is you're going to keep taking the derivative of the top and the derivative of the bottom until you actually come up with a number. Once you have a number, and I'm talking not 0, a non-zero number, on either the numerator or denominator, stop. So if this happens, actually it won't happen that way. It'll be more like you'll get a number down here and something up here, then you just stop. Okay? Now, basically, the way to understand this is to practice this. So let's practice with some examples. And follow my steps, and you'll see how cool this is. Now, these are the two examples that I had shown you before. So we're going to do these with L'Hopital's. So first of all, I plug in this 0, and so sine of 0 is 0 over 0. So now I know I can use L'Hopital's. So I can do the limit as x approaches 0. And then we take the derivative of the top, and the derivative of sine is cosine of x, and the derivative of the bottom is 1. So I know I have to stop because I have a number. Now plug the 0 in. What's the cosine of 0? Well, the cosine of 0 is 1 over 1, or my limit is 1. Isn't that cool? I don't have to make a table. I can just do that. All right, the next one, same problem as we had above, but we factored, but now we're going to do L'Hopital's. Let's see, I put a 3 in there, I get a 0 over 0, so I know L'Hopital's will work. So I do the limit as x approaches 3 of, take the derivative of the top, is 2x. Derivative of the bottom is 2x minus 1. Now when you get here, you substitute in the number now and see if you can work. And once I do, I have a 6 over 6 minus 1, or 5. And isn't that what we received before? So there's my limit, 6/5. Isn't that cool? That's how L'Hopital rule will work. Okay? Let's practice another one. Okay? The limit as x approaches 0. So when I do this one, I put the tangent of 2 times 0, or the tangent of 0, which is 0. This is the natural log of 1 plus 0, or the natural log of 1, which is 0. So now I know I can use L'Hopital's. So I say the limit as x approaches 0. And remember, you have to write limit until you come to it. And we're going to take the derivative of the top. Well, the derivative of the top is, the derivative of tan is secant squared, so I'm going to call that 1 over cosine squared. Then when I take the derivative of the inside, which is 2, so I'm just going to write it all as one thing, and I'm going to say this is the same as saying 2 over cosine squared x. So again, I took the derivative of tan, which is 1 over cosine squared, times the derivative of the inside, and I just wrote it like that. All over the derivative of natural log, which is 1 over 1 plus x, and then you take the derivative of the inside, which is 1. Now, plug a number in. Plug the 0 in to see if it works. So cosine squared of 0, or cosine of 0 is 1, so it's 2 over 1, so the top is 2, over, if I put a 0 in here, 1 over 1 is 1, so my limit is 2. Okay? Now let's try this one here. So I have the limit as x approaches 0. I'm going to put a 0 in here to see. Sine of 0 is 0 minus 0 over 0, so everything's 0 over 0. Please make sure you show that. So let's try L'Hopital's rule. So I do the limit as x approaches 0 of, now the derivative sine is cosine x minus 1 all over 3x squared. Now, as soon as you do that, you try plugging in 0 in. So I do. Cosine of 0 is 1. 1 minus 1 is 0. Oh, I still get 0 over 0, so I have to keep going. Okay? So this equals the limit as x approaches 0. So I'm going to take the derivative again. So the derivative of cosine is negative sine of x. And the derivative of 3x squared, oh, excuse me, the derivative of 1 is 0. And then the derivative of 3x squared is 6x. Now let's try plugging this in. So I do. 0, the sine of 0 is 0, and I'll still get 0 over 0. Alright? So let's keep going. The limit as x approaches 0 of the derivative of the top, so the derivative of negative sine is going to be negative cosine of x, and the derivative of the bottom is 6. Now I know I can't go any further because I have a number here. So I'm going to plug the 0 in there. So I have negative the cosine of 0, and the cosine of 0 is 1, so it's going to be negative 1 over 6. That is my limit. Don't you just love L'Hopital's rule? You can keep doing this until you get to the limit. But once you get to a number, you need to stop. Okay? Let's try a couple more. Ready? Plug the 0 in. Cosine of 0 is 1. 1 minus 1 is 0. And to put the 0, I have 0 over 0. So let's do the limit of this using L'Hopital's rule. So the limit as x approaches 0, and then take the derivative of the top, which is going to be derivative of cosine is negative sine, but since it's already a negative, it's positive. And the bottom is going to be 2x plus 3. Now, if I plug this in, I get the sine of 0 is 0. But then when I plug this in, I get a 3. So my answer is 0 over 3, or my limit is actually 0. Now, I want you to be careful because actually I've had kids keep going and keep going. No, no, no. Once you plug this in, after I put the 0 in that spot here and I get a 3 down here, you're done. Don't keep going, because if you keep going, I had a student who kept going until they had 2 and they didn't come out right. So you have to stop as soon as you plug that in. Okay, let's try this one here. 0 in here, sine is 0, 0, so I have 0 over 0. So the limit as x approaches 0 of 3, and the derivative of sine is cosine, so it's going to be minus cosine of x all over 1. I know I'm going to stop because I have to. I have a 1 down here. Put the 0 in there, so I have 3 minus the cosine of 0, or 1, so 3 minus 1 is 2 over 1, or my limit is 2. I always feel bad when I teach limits in the early part of the year because I want to show you this, but you haven't learned derivatives yet to show you this cool way to find limits. Okay, let's keep going. Let's practice some more. Okay, I have this one right here. Radical 1 plus x minus 1, so I'm going to plug the 0 in here. So I have radical 1 minus 1 is 0 over 0. So I have the limit as x approaches 0. Now remember, This is the same as saying 1 plus x to the 1/2. So when I take the derivative of that, it's 1/2, 1 plus x raised to the negative 1/2, and the derivative of negative 1 is 0, all over 1. So I know I'm not going to go any further. Let's plug the 0 in here. So I have a half, okay, times, now if I put a 0 in there, I have 1 raised to the negative 1/2, which is still 1. So the whole thing comes out to be a half times 1, or 1/2. So that's the limit. Neat. Okay, I have another one down here. They look really complicated, but they're really not once you take the derivative. So I'm approaching 0, so I plug a 0 in there. I have 1 minus 1 is 0, minus 0 over 2, so this is 0 over 0. So we can go sideways as long as you say the limit as x approaches 0. And let's take the derivative of the top. Again, this is 1 plus x raised to the 1/2. So this is 1/2, 1 plus x to the negative 1/2, minus, and this is the same thing as saying a half of an x. So it's going to be minus a half all over 2x. All right. So I'm going to plug in the 0. So I have a half times 1 plus 0. So I have, that comes out to be 1. 1 times a half is a half. Half minus a half is a 0. Oh, I still get 0 over 0. So I'm going to keep going. So it's a limit as x approaches 0 of, now I'm going to take the derivative again. So I do negative 1/2 times 1/2 is negative 1/4. 1 plus x to the negative 3/2 now, because I have to subtract 1. This negative a half goes away. Now I have a 2 in the denominator because I take the derivative of that. So I know I'm done because I've reached a number. Let's plug the 0 in there. So I have 1 times negative 1/4, which is negative 1/4 on the top divided by 2. So it comes out to be negative 1/8. Okay. So now we've practiced some problems that I'm approaching a number of sorts. Now I want to do some with infinity because I think that causes a little bit of a problem. So we're going to use an indeterminate form of infinity over infinity. So these approach infinity. You do the same things, but people aren't as comfortable with them. So I want to make sure that you are. So we're going to practice some infinity ones. Now, remember when I do this, it's basically huge over huge. And remember, just recall, that if I take a number of anything and divide it by huge, it essentially approaches 0. Don't forget that. Because if I keep cutting a number into larger and larger pieces, it gets smaller and smaller and smaller. Okay? So let's look at this. If I put infinity here in the next spot, this is infinity, and anything e to huge is going to be huge. So I have huge over huge. So I can use, so this is huge over huge. So I'm going to use L'Hopital's rule to do this. So I'm going to do the limit as x approaches infinity. Now the one thing about this, it's very difficult to substitute huge, but you understand. So if I take the derivative of the top, or the numerator, that's a 1, and the derivative of the bottom is e to the x. Now, here's the thing. I have a number here, so I know I'm going to stop. So I say, okay, if I put this is really huge. E to the huge is really huge, so I have 1 over huge. If I have 1 over huge, that's essentially 0. Essentially 0. So that means this is going to be 0, because if I take a number and divide it by huger and huger numbers, then there you go. Okay? Here's this one. All right? Remember your horizontal asymptote as x approaches infinity on this one. So I look and I put this here and here, so I still have huge over huge, because I'm getting bigger and bigger numbers over bigger and bigger numbers. So if I do the limit as x approaches infinity, if I take the derivative of the top, it's 2, and the derivative of the bottom, it's 5. So my answer is 2/5. Now, remember and recall horizontal asymptotes, because look, if I were to circle those and cancel out, wouldn't I have 2/5? And see how L'Hopital's rule makes it so simple? Isn't that neat? 3, here we go again. Now, I can tell by looking at this that this is going to be 3 is the answer, but I want to show you how L'Hopital's, this is the horizontal asymptote check. So right there, I know that's 3. Okay, so I'm going to erase that so we don't make a mess here. But I look and if I put huge in there, I'm going to have huge over huge, because they're both polynomials. So I'm going to do L'Hopital's rule. The limit as x approaches infinity is going to be 6x minus 4, because I'm doing the derivative of the numerator over the derivative of the denominator. Now if I put huge in here over huge, I still have huge over huge. So I'm going to keep going. So I just say the limit as x approaches infinity of 6 over 2, which is 3, which is what we said to begin with. So L'Hopital's rule does work. Now I have this one here with infinity. The natural log of a huge number is huge, and 2 times the radical of a huge number is huge, so I can do L'Hopital's. So the derivative of natural log of x is 1 over x, and the derivative of this is x to the half, remember, is a half times 2 is 1, and it's going to be x to the negative 1/2. So if I put huge in here, I'm going to essentially have a 0 in the numerator, and this is going to be over huge, because if I put huge in here, so I have 0 over huge, which is basically 0. Okay? So now I've shown you how to use L'Hopital's rule. It's really neat, it's fun, it goes by fast. I do want on these last 3 is to recall and remind you about vertical asymptotes. So vertical asymptotes I want you to think about with these. If you see that I'm approaching to the right or left, that should be a sure sign that maybe there's a vertical asymptote. If I put a 0 here, I get basically 0 over 0. Okay, so I'm going to try doing the limit here and use L'Hopital's rule. So I have x approaching 0 from the right, okay, and the derivative sign is cosine of x over 2x. So if I put a 0 in here, I get a number, okay, over 0. Remember, when I get a number over 0, that means you're either approaching infinity or negative infinity, so you have to actually look at the graph. If you did, you see that there's a vertical asymptote here at 0, and if you approach from the right, you're going to infinity. Now here's the exact same function, but we're approaching from the left, so the work looks the same. It's 0 over 0. I have x approaching 0 from the left. I take the derivative of the top over the denominator, the derivative of the denominator, excuse me. I still get a number over 0, okay? So this actually, when I approach from the left, this approaches negative infinity. So basically this graph, if you were to look at it, is it has a vertical asymptote where when you approach it from the right, if I can get to right here, so here's the graph. When I approach it 0 from the right, it's going to go to infinity. If I approach 0 from the left, it's going to go to negative infinity. So the graph might look like that. I'm not for sure, but that's what that looks like. Okay, we'd have to graph it and look at it. The last one I want to show you is to be careful, and if I put 0 in here, I get 0 over 0, and we're going to use L'Hopital's rule, the limit as x approaches 0, and we're going to do the derivative, so it'd be sine x over 1 plus 2x, and when I put the 0 in there, I get a 0 over 1. So again, 0 would be this because I've hit a number. So basically that's the notes with this. So what you have left here is some labs to do. I'm going to have the answers in class for you, so go ahead and practice the labs, and then you're going to have bookwork. And the assignment in the text is going to be this. So you're going to complete this lab, these problems, and the text assignment is page 224 through 225, and you're going to do 1 through 35 all, and you're going to omit number 4 for me. So that when you get to class on Tuesday, you are actually going to, I probably shouldn't say the date so I can use this again, but when you get to class next time, what you're going to do is going to be practicing these labs and working on the text assignment, and then when I see you, we'll go over anything you might need help on. Okay? So that's L'Hopital's rule.